Okay, we'll start now. Can you hear me, everybody? Can everybody hear me on that side? Okay, I will have your exams graded by next Wednesday probably. So you can come see me in my office if you want to see the score. I will post them also on Brightspace for you. First, before I get started, are there any of you who are distant? Do any of you have any questions? Anybody? All right, let's just start then. Please, someone speak up. Tell me you can hear me.
We can hear you.
Okay, good. Thank you very much. All right, very good. So basically what I'm going to do is essentially continue with the next chapter, and there will be an overlap. So stuff on the next test will include stuff from the chapter 7 a little bit that fits. Okay, so basically we're going to get into more of the shapes and other things like that and talk about the different aspects of orbital theory and such. And I'll try to keep it as visual as possible and away from the quantum stuff and such like that that may get many of you lost. So basically what I want to do now is just continue with the next set of slides. And what I want to do first is introduce that by using the end of this set of slides just to finish off to see here regarding, okay, that's bond enthalpies. That's not very helpful. Okay, so I'll close this and then we'll go to the next one here. Okay, and it is chapter 10, and it's chapter 10 in Chang, and basically I will put that with notes and such like that also when we have this. Now, molecular geometry, this is the next part, and this is enough to finish your things essentially regarding those worksheets I passed out to you, those of the experiment 13 as well as the other one. So what I'm going to do now is start the PowerPoint and then share it with everybody here. And we're going to talk about the different models first. So basically what I want to do now is to share the screen with you here. Okay, can everybody see the screen there? Can everybody see the screen? I'm sharing it with you.
Yes.
Okay, wonderful. Okay, so now we're going to talk about molecular geometry and such like that. And basically what I addressed a little bit to kind of give you a heads up on, if you have a structure that looks like this, oops. If you have a structure that looks like this with a nitrogen here, a double bond, and then a single bond, and there are 3 resonance forms, and this is a -1. This I already talked about is what is called trigonal planar. It's flat. And we're going to talk about the other ones related to it later. So I'm going to stop the share for a sec. This isn't right. I can't write it on it very well. Just a minute. I got to do the right one to do this here. Hold on a minute. I'm trying to fix the slide so I can write on it properly. Okay. Okay, I'm going to go back to sharing the screen with you again. Okay, hopefully this will work now. Okay, and basically the key thing about this is I want, oops, going back here, is essentially you have structures that look like this, like the nitrogen here, and then you have two resonance forms like this. I've also showed you structures that look like this, okay, or like this, and these are linear. And so then there's going to be some other ones that we'll talk about in a moment. But basically the key thing about covalent bonding is they like to be orderly, they like to be consistent, and they like to fit it so it has the most stability. In other words, you don't want a long chain of things that would kind of flop around. That's the key thing here. The more it flops around, the quicker the thing will fall apart, because energy has to do with energy of motion when you're talking about kinetic energy. And essentially, if it flops around, it's going to break. Just like if you take a long string and kind of flop it around, it'll be weaker than a shorter one or a more compact one. So basically, a string isn't a good example. I guess a wet noodle might be a better one. But the point is, again, it's a situation where it all has to do with stability, and compactness is more stable. So basically, we're going to talk about one model in particular, and it's a very good one, the valence shell electron pair repulsion model. Now, first thing, let's go through the terms here. What is the valence electrons? What are the valence electrons? Yes, very good. So essentially, you get up to 8 electrons in the outer shell. Okay, so it's talking about the outer shell here, the valence shell. Now, electron pair repulsion, what does that mean? When something is repelled. Yes, okay. So if you've got an electron pairs here in one orbital and another one comes nearby with another atom, you got an X and you got a Y here, what's going to be the tendency for those to happen if they just come next to each other? They'll go as far apart as possible, okay? So essentially we're talking about essentially moving them across, and it's a model because it sort of represents kind of how these things work. So essentially, we have a model that kind of represents real life. Now, predictive geometry from the following electrostatic repulsions between electron pair bonding and non-bonding pairs. So let's just look at some examples. The first one is AB2. Okay, what's an example of a compound that's AB2? Can anybody think of one? Yes, CO2, okay? So essentially you have one in the middle, or it could be even simpler than that. It could be like, beryllium, BeHH, like this, okay? So how many atoms are bonded to the central atom? This is a covalent bond, just so you know, this is covalent. How many atoms are bonded to the central atom? 2, 1 on each side, okay? How many lone pairs are there? None, okay? And the arrangement of the electron pairs there. These electron pairs are here and here. So what is that? What does it look like there? Linear, very good, okay? And so the molecular geometry is going to be linear, okay? So essentially it's following a set of organized things that kind of sets it up. So essentially you have that, okay? Now, what's the difference between this and say okay, we'll just go to another example, and the next one, I'll just finish off the slide here for a sec, so you can see where I'm going with this. The number of bonds, 2 in there, the number of lone pairs is 0. The arrangement will be linear, and the molecular geometry will be linear, okay? And a great example of that is beryllium chloride. Where are the electron pairs in beryllium chloride? Where are the electron pairs in the beryllium chloride? Andy, will you volunteer?
What was the question again?
Where are the electron pairs in the beryllium chloride? Are there any on the open electron pairs? Are there any on the beryllium?
Yeah, there's a single bond to chloride, a single bond to chloride. There's two.
Yeah, okay, but are there any other lone electron pairs? No, okay.
No.
The other ones are around the chlorine. So essentially you have the others around the chlorine, and when they're around the chlorine, they have kind of like a lobe associated with them. And let me go back to the ink. Electron pairs will be in a kind of a lobe sticking out like this. Okay, so they'll want to stay as far apart as possible. And basically the only way it can do that is if it's 180 degrees apart. Okay, so basically they want to stay apart as possible. Now, why is it valence shell electron pair repulsion? What's the electron pairs that are repelling each other? Trying to keep it spread out in a linear form. In that structure, where are the electrons repelling each other? Well, they're the top and the bottom of the chlorines. So basically those are like clouds. They will try and keep it away from the other chlorine as much as possible. You will not have a structure that looks like this. Be with a chlorine up here, sorry. Be with a chlorine there, and Be with a chlorine there. It's not going to happen because these will repel the other over there. Okay? So essentially the nature of the energies flattens it out. That's the key thing you're dealing with. Okay, so essentially you've got a series of things that work together with this. My seat is falling down on me. Okay, so let's go to the next slide. There are no lone pairs of the central atom. And essentially you have a linear arrangement pair of that. And so the next one would be AB3. What's a good example of that one? Move along the periodic table. Look on the example. What do you think is a good example of that one? What? NO3? Not necessarily. Okay, and I'll show you why in a minute. Just move along the periodic table. What's next to beryllium? Boron. Okay, so boron, how many does it have around it? 3. Very good. Okay, so essentially we would have something that would be boron trichloride. Okay, and where are those going to want to stick? They're going to want to be as far apart as possible. Okay, are there any extra electron pairs in the boron? Are there any electron pairs in the boron? No, they're already taken up. This violates the octet rule because there's only 6, but there's only room for 6. So it's no problem there, okay? So essentially you have that one, essentially this. So we move along. You have 3 atoms bonded to the central atom, no lone pairs again. And this is called trigonal planar. And it's flat like that, and essentially you can see that if you put the boron in the center with a chlorine over here, a chlorine over here, and a chlorine down there. Now you mentioned the nitric nitrate ion, right? That's a little bit more, but with that one you have a double bond like that, another one kept up like that, another one. So it's still trigonal planar, but you have 8 electrons around the center atom. So that's a different thing, but it's still trigonal planar. So yes, in a way you're correct. So you're thinking ahead, okay? Any questions? Okay, and then the molecular geometry will be trigonal planar here. So essentially you have that next one there with a trigonal planar structure. Okay, and it'll be kept flat because they want to be 120 degrees apart from one another. Does everybody see that? Any questions of those who are virtual? You understand where I'm going with this? Okay, so let's go to the next slide. Boron trifluoride is one example, okay? You got the fluorine here with 6 electrons unbonded. They'll want to stay as far apart as possible. And what is the only way for them to stay as far apart as possible? In this form, because if you have it, if you bend it or something like that, it'll get closer to one place or the other. Okay, it's all about trying to get them as far apart as possible. Okay, and when they take a picture of it with SEM or other structures like this, they can really see there is a planar structure of them. There are ways to take pictures of these things, and believe it or not, the models work. That's what's cool about it. And I think it's just wonderful proof of God's design, that he likes creating such beautiful things, okay? And I say that as a chemist, but also as a person who enjoys art, so to speak, God's art in a way. Okay, so the next one would be AB4. Now, what's a good example of that? And somebody, move along your periodic table. What is the next element just past boron? Those of you distance, any volunteers, those distance ones, volunteered to say, what's the next one next to boron, going to the right?
Carbon.
Carbon, very good. Okay, so you have a carbon in the middle, so you'll have 4 around this, so the carbon will look like this, there, 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 and there. But it is not flat, it'll be in a 3-dimensional structure. And I can't really show that on the paper. Your book does have a nice picture of it, and we'll get to that. But the key thing is, essentially, it's a very logical thing. As you move along the thing, essentially you get a series of different ones related to these things, okay? So there are 4 there. How many lone pairs are on the central atom? 0, they're all 0 on there. And again, it's called tetrahedral, and it looks like that. Okay, their art on this is much better than mine. Okay, now does everybody see that each individual atom on the tip of whatever else, they're as far apart as possible? Why is it not flat? Why is it not flat? Why is it in this pyramid form? Because there'll be strain in it. Essentially, there'll be strain in it that will cause some of those the hydrogens to be closer to one another, okay? The only way for them to get as far apart is to be at that angle in what they call a tetrahedral form, okay? And then you have the tetrahedral there with the A, B, whatever across that. And a good example there is methane. And essentially, you have the hydrogens here, hydrogen there, hydrogen there, hydrogen there, and this is the carbon. Okay, now we go to the next one, AB5. Okay, now what's the next element along the periodic table next to carbon? Nitrogen. And what does it look like? It looks like this. Nitrogen, you put the dot structure here with a bond there, and a bond there. And ammonia is a great example of this. Okay, there are 5 electrons around the central thing that the nitrogen has. How many atoms are bonded to the central atom? In this structure, how many atoms are bonded to the central atom? 3. Okay, and you've got this electron pair up here. There's nothing that can bond to that. Okay, but the thing that's cool is if you add a proton to it, you get this, NH4 plus. So what structure does that become?
Ammonium.
Yeah, it's an ion, but what structure does it come? Instead of being, it's like AB4, it's now tetrahedral. Okay, you add a proton to it, which would make the ammonium ion, okay, in structure, and it'll be tetrahedral. But if you erase it and put the thing in, and this kind of shows here, if you erase this and erase that and put the things back on it again, this electron pair this is going to be different because this is just going to be a lobe. It will not be a hydrogen. So essentially it won't be tetrahedral. It'll be a modification of that. Okay, and so it's 5. There's no lone pairs in the central atom, and it's called trigonal bipyramidal. And that's the 3-dimensional structure for it. It's called trigonal bipyramidal. Yes. What? Oh, okay. Oh, yeah, you're right. Good. That's another example. And an example of that would be you move along there, and essentially this would be like phosphorus pentachloride. Sorry. You put phosphorus here, Cl, 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 like this, Cl, and then you have one Cl there and another Cl there, and essentially those would be 5. Okay, so I went in a different direction regarding my own understanding of the model, because I essentially had there no lone pairs, one lone pair, but that's a modification of it. So very good thinking of that. Okay, so basically this book goes a little different. This is called trigonal bipyramidal, and an example of that would be PCl5. Okay, and we'll talk about how that forms in a minute. But this example here, phosphorus pentachloride, and essentially the only way they can be as far apart as possible from one another is the same way. Okay, but if it's the other form with electron pair at the top, it'll be a slightly different form. Yes. Well, yes, it breaks the octet rule, and we'll talk about that in a section coming up, because it forms what's called a hybrid orbital. Okay, and basically that's what we're getting into, hybrid orbitals, because there's a shift, and but we're just kind of addressing the model first. Okay, the next one is AB6, and how many things would be around that one? Well, there would be 6 around that, again with 0, and this is called octahedral. So they're kind of teaching you the different things there. An example of that one would be sulfur hexafluoride. Now, the way I like to do this, if we go back on the slides, let me go back on here. If you're asked to give the Lewis dot structure for PCl5, how would you do that? So let's just start it off. How would you do that first? Yeah, you put the P in the middle, okay? And this illustrates why phosphorus can have 2 compounds of chlorine, and why you use phosphorus trichloride or penta, okay? And you can put 1 chlorine there, 1 chlorine there, 1 chlorine there, and that's 3. That is a legitimate compound. This has 1 electron pair there, so it's a slightly different thing. It's a modification of the tetrahedral, okay? And we'll talk about that in a minute. But basically here, what happens is you can kind of see that this splits, and you get a Cl there and a Cl there, because the electrons move around, and they just happen to move into the empty p orbitals, no, the empty d orbitals that are available for it to enable them to round and form what's called a hybrid. And we'll talk about those hybrids also, okay? So basically you essentially put the phosphorus here, you have the chlorine here, chlorine there, and then you have a dot there and a dot there because they spread out, but these modify, and then you get a chlorine there, and they all spread out around it just like that. Does everybody see how that works? Alami, do you see how that works? Kind of, it's like you use that little form. And the benefit of the way I taught you how to do Lewis dot structures is you can easily put a little line in there and have them split like that. Okay, and so basically we go to the next one there. So AB6, what's the next one along the thing here? The thing, you have to go to phosphorus and sulfur instead of nitrogen and oxygen. Nitrogen and oxygen, they're too small. They're too small a ball. It will not split. You do not have those d orbitals available for them, okay? So the next one along the line next to phosphorus is going to be what? Sulfur, okay? And there's 6 around that. And the thing that's cool about sulfur, you have 6 there, And we're going to do that, react that with fluorine too. This is fluorine here and fluorine there, right? You see the two fluorines. This is one of the compounds of sulfur. It's called sulfur difluoride. Okay? What happens if it splits here? Well, you get another fluorine here. Oh, sorry, we got closed. It closed the screen. Just a minute. I gotta start this thing again. Okay, I'm gonna share the screen again for you. Sorry about that. Okay, you got the sulfur here, and essentially with the sulfur here, you have these electrons here to do, and these split off and can form another one. So you can have 4 around it, and then these two will split off here and off here, so you end up with SF6. Okay, so essentially that's the next one along the line. So essentially you've got the different ones working for each along each part. Okay, so basically we'll just go to the next slide now on this thing here. AB6, you have 6 there, 0. You have an octahedral. Again, they split here. Oops. They split here and here, okay? And then you have a fluorine there and a fluorine there. And again, they're forming those hybrids also. And you got what's called an octahedral structure. And that looks like this. And the angles around all of them are 90 degrees. Okay? So these are the different examples for the electron pairs around the central atom with some simple molecules and ions of which there are no lone pairs. And you can have one that have 1 lone pair or 2 lone pairs also, and they are modifications of the other structure, and we'll talk about that next. But this is a nice chart to help you work on when you're working on the homework. Read the chapter first, look at the little problems along with the little models, and then draw on your paper. And please don't use the computer to draw whatever else. Use blank paper and practice drawing this stuff out. You'll really get the hang of it much better. Okay. Okay. So basically, that's that. Now, before I go on, I just wanted to mention some of you that are virtual. I am passing back the second exams to the students that are here today. You can come by my office and pick up your exam. As I told the other earlier students, there was one person that made it up last week, and no, there were some made it up earlier, and then basically there was some other in quarantine that I thought would need to make it up, so that's why I kept it until this point. So basically, that's the thing. But you can come pick it up in my office. It'll be available to you today, and I'll be glad to go over it with you. Okay. Now here's some examples of the different values here, where you have this, and this is a new thing here. Here where you have this methane, you have 4 carbons around it, and then here you have 1 electron pair on the nitrogen. And notice that that structure is going to be different. Why is this one, why is number 2 different from number 1? What is at the top? Is it a hydrogen or is it something else? It's a lone pair, so it's going to have different angles. The lone pair isn't as effective at pushing it down. But if you put a hydrogen on here and made that the plus, that would be the same as that, and the things would shift. So essentially, it does have that value. Okay, and this describes why the other tetrahedral form here with these lone pairs. This is water, and that describes why water is not a linear structure. Some of you may be tempted to put water out like this and say, this is linear. It sort of looks linear, but remember, you got to remember it's a 3-dimensional structure, and it won't be, because this electron pair will repel the hydrogen, etc., because that hydrogen will not want a thing. They will shift, but they will not want to bond with the hydrogen because that's already bonded. Okay, so basically all of these are variations of the tetrahedral structure. They're just different variations to them. So I'm going to erase this here so you can see that there going on. Okay, so here you got a lone pair versus lone pair repulsion. Then you've got a lone pair versus a bonding pair. Okay, the lone pairs on the left are in the bonds themselves. Then you've got the lone pair versus the bonding pair repulsion. And then you've got bonding pair versus bonding pair repulsion there. And 2 extra electrons associated with 2 extra electron pairs associated with the oxygen that are there. Okay. And the angles change. Now, the next one, BSAPR, where number of bonds to the central atom, the number of things, that is trigonal planar. And essentially here, the E refers to this electron pair associated with this, okay? So basically, there are 2 to the central, you have 1 lone pair associated with that, and this is also trigonal planar, but it's a different kind of trigonal planar because you just have that electron pair there instead of the other one. And SO2 is one example of this, okay? SO2 looks like this. If you put the sulfur like this, and then another oxygen over here, 1, 2, 3, 4, 5, 6, and then another oxygen over here, 6, and then essentially you get a bond that comes off of it like this. You essentially form one double bond with this sulfur there, and then a double bond on this part, and then a violation of it. You have this electron pair there, a double bond O there, and a double bond O there. Though that is just one possibility of the things, or you could have what is called a kind of resonance form that looks like this. You put the sulfur here, and then it combines with an oxygen. You have the oxygen over here that also has 6. You get a double bond associated with that, and then you get one other there, and you've got resonance forms. So this has a formal charge of +1, and this has a formal charge of -1, and then, but you have 2 resonance forms, so it fits into this very neatly, and it can be represented in that structure, the SO2. Yes. The E represents the lone pairs on the central atom. Okay, on the central atom there. And here you got AB4, and then with an E, and then you have 3 though, 1 there, and you can see this with the tetrahedral again. And the example of this would be ammonia, where you have this, and then hydrogen here, and hydrogen there. And this is also a tetrahedral structure, but it is called trigonal pyramidal instead, okay? It is a tetrahedral. Now, for general chemistry 1 students, if you're asked what is that structure called, if you want to call it tetrahedral, you can, but it's called trigonal pyramidal. Why is it given a slightly different name in its molecular geometry? And I would like you on the worksheet for the experiment number 8, I would like you to put trigonal pyramidal because that's the official name and you got the book to use with it, okay? But if it's on a test, it is a variation of tetrahedral. Why is it a variation of tetrahedral? And it's almost an atom, but it isn't. It's just the electron pair sticking out of it. Okay, so essentially you have the trigonal pyramidal. Now, AB2E2. You have 2 atoms bonded to the central atom, 2 lone pairs associated with that. It looks like this. It is also a tetrahedral form. Now, what's a good example of this one? Move along the periodic table again. What's a good example of this? I used ammonia for the previous one. What is a good example for this one? AB2E2. Water. Okay. You have an oxygen here. You have hydrogen there, electron pair here, and electron pair there. 2 electron pairs. So water is a great example of that. And that is called bent. But if on a test you said it was tetrahedral and then put a qualifier next to it, it's a little different. Or you could use bent for it. It is not linear. The reason it's not linear is because of these electron pairs. Okay? Does that make sense to everybody? Any questions? Those of you distance. Nick, you have a question? Anybody distance have a question?
I'm good, Dr. Douglas.
Okay, you're following my logic. Wonderful. Okay, very good. Okay, so now AB5, number of things and 0 lone pairs. Again, the example of that one is PCl5, when you have all of them. Okay, you could also have AB4E, okay, where you have 4 bonds around it with electron pair, one electron pair, and this is trigonal bipyramidal again, and it's called a distorted tetrahedron, but I'm not going to ask you to memorize that, okay? But if the worksheets ask for you to do that, then that's where you put that in. Okay, so does everybody understand how to do that experiment 8 worksheet? That is the lab, the way it's going to work is this week, the people that come in person are doing the metals and the halides lab, and you folks who are virtual are doing the experiment number 8. And that involves these molecular geometries. It's all related, also related to that experiment 13 I gave you for the lecture exercise. So these are the geometries. So now you can fill in that part of the experiment 13 that you have there, okay? And then the next one, AB3E2, where you have 3 around it, 2 electron pairs, and essentially you have trigonal bipyramidal again, but it's called T-shaped. And there'll be an example of that also coming up. But basically, those are covered when we get fully into the hybrid orbitals, of which is the next section. Okay, and then lastly, AB2E3, you have 2 in the center things there, and then you have trigonal bipyramidal again with this, 3 lone pairs, and then you've got a linear structure. And essentially with this, you've got the hybrid orbitals again forming, but there's a bunch of different examples about how that would occur. Say, for example, if you had if you had, I don't remember offhand a good example, but we'll come to it. And then AB6, AB5E with 5, 1, and that's octahedral with an electron pair, and that's called square pyramidal. And again, it's square pyramidal because it doesn't have an atom to go in the last part. And then AB4E2, you have 4 in the center, and then 2 electron pairs. That's octahedral, square planar, like that. And there's a bunch of different examples there on that chart. Yeah. But again, all these more complicated ones, if you're asked on a test, saying these are octahedral are just fine, okay? So if you're given a structure like this, that basically Xenon Tetrafluoride is like this, where is xenon on the periodic table? It's a noble gas. How many electrons does it have around it? 8. So let's put 8 around it. Xenon. 1, 2, 3, 4, 5, 6, 7, 8. Now it's very big, right? How would it get 4? How would it get 4 fluorines off of it? where are they going to go? You split it right there and right there. So essentially you have a fluorine there, fluorine there, a fluorine there, and a fluorine there. Now, why is that square planar? What keeps it flat? What keeps it flat? Well, you got a 1 electron pair at the top, the other electron pair at the bottom, and the 4 fluorines around. They're all going to want to stay as far apart from one another as possible. The fluorines particularly. Okay, so they all repel apart and it ends up being flat. And that is really, really appropriate. Okay, you could go back to the other one with this one there, Br with bromine. You put bromine here. This is an example of bromine, 1, 2, 3, 4, 5, 6, 7. You put a fluorine first there. How can you get 4 more fluorine to come off? Where are they gonna attach? Well, here you just have a fluorine here, a fluorine here, a fluorine here, and a fluorine there. See? Okay, very straightforward with that. And then you go to the earlier one where you have AB6 like this. This is I3, where you essentially have iodine here, 1, 2, 3, 4, 5, 6, 7, and you've got essentially you have 3 electron pairs. You have another iodine that goes on the top part. You have an iodine here, which bonds with this. Another iodine there, and then you essentially could have another iodine on the other end, iodine with a -1. Sorry, my art isn't very good, but you can see that on the right and see how that forms that structure for the trigonal bipyramidal structure. And then you go back to the T-shaped chlorine trifluoride there to get the 2 things. So there are examples given on the right. And then going back there, you can see the other one too with that structure, a different one, a distorted tetrahedron with that. Okay, now AB4E2 like this, octahedral, and xenon tetrafluoride there, and those are different examples. And I believe there is one that given up there that's SF4 there, where essentially you have the S, the sulfur, and then you have fluorines sticking off of it, essentially in the other places, and they come from what are called hybrid orbitals. Now, predicting molecular geometry. Well, you draw the basic molecular structure for the molecule. You count the number of lone pairs on the central atom and the number of atoms bonded to it. Use VSEPR to project the geometry of it, and then write that. So what are the molecular geometries of SO2 and SF4? So let's do one example. Well, SF2 looks like this. Are there resonance forms associated with that? Yes, okay. What's the other resonance form? The double bonds on the other side. So you could have the double bond over here too, and this electron pair at the top shifts it. So essentially you have the electron pair there and then the other one over here, and this is this now like this. This is a formal charge of -1, this is +1, this is a +1 formal charge, this is -1. The whole thing is 0, but you've got all of the electrons flowing around through the thing. So essentially it looks like this with the sulfur, this electron pair there, the oxygen going over like that, the other oxygen like that, and it kind of flows through that. And so what structure is that going to be close to? What kind of structure does that look like? If you got it all bonded up like that, what kind of structure would it look like? Trigonal planar, very good. It's one of the variations of it, okay? SF4 is another example where you have the S and then you have the 4 fluorines sticking off of it. And essentially that would be a different one, okay? So this would be called bent, but it is also trigonal. It is also a form of the, because these double bonds are shifting along it, but it's a different form of bent. And that's a distorted tetrahedron. Okay, so basically what I'd like you to do is finish the worksheets and work some problems in this section using the model. And there are sample problems at the end of the chapter for this section, essentially using the model to predict them, and just practice, 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 and we'll continue with this on Monday. Any questions? Okay, very good. We're done for the day. I'll see you all later, and please come pick up your exam. Okay, any questions? Those of you at distance. Okay, Jordan? Yes. Come get it, things. These are the numbers there. The total was 41, and add 15. That was the curve, okay?
Okay, thank you.
Gabby? Riley? Okay, you are,
Haley.
huh?
Haley.
But the curve, that's just the wrong number. The curve is done in that. So your name?
Anna.
Anna West?
Hewitt.
Oh, Hewitt.
This is the wrong number?
Yeah, but I believe so. It's a 70 where it might be the curve. I don't remember,
Okay.
but basically they're broken down that way. You're Anna.
Hewitt. Thank you.
Mm-hmm. And the key is online regarding the multiple choice parts.
Okay.
Yes.
Question: is there any way I could see my grade from my lab test that I took? I had
Yeah.
a lab yesterday, but
Yeah, I have it in my office. I'll show you.
Thank you.
Just a sec.